And thank you, Professor Yu, for leading this workshop. And this actually recall my whole memory with the guidelines and the very kind and continuous support from Professor Yu and with another leader, Professor Chen Zhang as well, and working on transfer from the data-driven algorithm-focused research to the domain-driven actionable knowledge discovery, and to really solve some of the problem and make sure what we deliver can really make some impact to industry. Could it be millions of dollars or billions of dollars saved for government, or could it be some social or other sort of like a benefit. So today I take this opportunity like to thank you, Professor Yu, and thank you, the workshop organizer, and particularly Charles, and all the team leaders, and for this leadership, and really appreciate that. What I'm going to do here, first of all, I briefly just to review what happened in the last 15 years almost related to this concept of domain-driven data mining. And then I just highlight a few things related to my team only, because I know a lot of things going on in the world, and particularly if we focus on domain specific application, and just a minute things to talk. I mean, also reviewing the community and some other things related domain knowledge. Of course, that's the important part, and how to involve domain knowledge into data mining or into machine learning, et cetera, et cetera. So that will not be my main focus here. And the main focus, the second part, I want to share some of my personal thought about some of the complexities and intelligence related to complex data, complex system, complex behavior, and particularly some, something related to the challenge related to the data or system behavior, the interactions, and all different sorts of heterogeneity and company relation, et cetera, et cetera. So and move on forward, and also share some of my personal opinion about some of the further opportunities there. So that's the main thing. And so the concept of domain-driven data mining was proposed, I think, in 2004, so a long time ago now, right? So a lot of activities happen, over time. So there's some special issues on the workshops, particularly very originally with KDD, and also always we have Professor Yu here and to drive this one guided, and I actually just do the labor work, and so there, and then the workshop moved to ICDM, and there are some special issues and tutorials. And at the corner, you see this one is with IEEE transactional knowledge and data engineering, and led by Professor Chen Zhang and Professor Yu, and also David Bell. So that's actually a special issue there on domain-driven data mining with TKD. And then, so a couple of years ago, and another special department with IEEE intelligence system on domain-driven actionable knowledge discovery at track a lot of papers, and there's a special department. And I think Treasury is organizing with some other leaders, organizing another special issue on domain-driven data mining with Journal of Data Science and Analytics. So there are a lot of things there, so we are interested that. So, and also like to mention some of the relevant reference, and of course, they are mainly related to domain knowledge, involvement into the data mining process, or domain-specific applications like data mining for business applications. The edited book is myself and Chenji and Professor Yu all together, and then another monograph summarize some of the main ideas and thinking about domain-driven data mining. So that's already 10 years ago. And so there are some other, papers, particularly like, this one talk about, the challenge and prospects of, of data mining, and particularly when we focus on the, the decision making or decision support. And so based on my experience in, working with industry, before I moved to UPS, I was a CTO working in industry. So particularly focus on BI, business intelligence. I got a little bit of experience observation about issues and the gaps, and so there's some reflection there. And this paper, we summarize some of the frameworks for making actionable knowledge discovery. So I mentioned a little bit. So one thing here is a framework as showing the corner to highlight not only just a normal thing related to data understanding and business understanding and those kind of things like modeling of course, and particularly want to emphasize the human machine or human mining system interactions, and that may be related to human-centered data mining, as Professor Joy Han, some other researchers promote that. And another issue is that so often we have to focus on in-depth modeling or in-depth data intelligence. What I mentioned that's 15 years ago, discover in-depth data intelligence. And that may mean so it not just come from the straightforward modeling. It may need to go through some other extra step on top of the initial results. And then particular thing I want to emphasize here is called actionability and how to define it and how to evaluate and how to enhance it, et cetera, et cetera. And eventually, we really want to have something that can solve some of the real problems in industry, in the complex system, and can be deployed and are really converting into decision support business rules or being incorporated into the business system. So those are kind of thinking to enable the process, and particularly related to actionability. So there are different ways to, of course, to assess, what do we mean by, actionability and how to evaluate it and how to enhance it and how to, test it and how to select it. So there are some process and develop and also linked to system support and to enable the actionability evaluation and optimization and enhancement, et cetera, et cetera. So some of the ideas and thinking there. And related to a key concept of what do we mean by actionability, a high-level framework is something like this. Typically, we focus on the technical objective side, but there are also technical subjective side as well. And typically, because we want to make sure this kind of discovery could be really helpful for business. So we have objective or subjective aspect to measure the business, impact of business, so what a change we can make and what a difference we make for business. So overall, put them together. So we have, the four parts related to, so given the input, so we have the pattern, that pattern needs to satisfy, either some of them or all of them. Of course, in the specific domains, we have to define and specify them. For example, for subjective in the capital market, when we make a algorithm to trade and high frequency trading, so we have to actually not only just calculate the support confidence. For example, we use a frequent pattern mining based approach to do the frequent sequential pattern mining of the trading strategy. But we also have to evaluate, something like Sharpe ratio, and also have to, check, more subjective, criteria like, beat the market. So beat the market means we have to beat the index. So that has to be quantified. So, but it's a subjective, measure. So those kind of things, we have to quantify them and form a framework, and so that we can actually, somehow not only make sure this kind of discovery is not only statistically important and significant, but also from business perspective that can really make difference. So over years, we summarize different kind of framework to support that. For example, so this one shows if we have multiple sources of data, or even one enterprise data that usually consists of multiple data sources or multi-model, multi-view, and each of them, so usually, we would not be able to integrate them or simply put them together into one data mart and then build one model on top of that. So that usually in the enterprise, environment cannot really make that. So what we usually do is that we would, develop, choose one of the data set or even just some of, samples there, and then we, based on the domain knowledge and the meta knowledge, and we develop some pattern from there, do some exploratory analysis. And that could be the, some of the sort of like a seed or guide and for us to further find the next, most relevant, data source or modality, and then to be combined with that and to further can have some sort of like, algorithm development on that, and then, build the patterns, and that pattern could be further, merged with other patterns identified, and then, further needed to be converted into something, that can be acceptable by business and could be integrated in the business system, for example, converted into, business rules. That's what we usually do in industry. So it's not only just the algorithm, but also, transfer that into sort of something can be integrated into the business system so that, the business people, they would not see the algorithm and then they can actually have their interface to interact. So there are many such kind of summaries, and another concept, and so we when we have the multi-source of data, for example, so we have the in the social welfare business, social security. So if we have the those people who receive the government allowance, we get their demographic, and of course we have the government policy or government arrangement on those people, and also the feedback or the response from the from those people. So we can find some interesting patterns called a pair pattern or cluster pattern or derivative pattern. So we can monitor the multi-aspect things, and have a bigger group like for 65 years plus, and then with different or on a different government arrangement, and then the risk level could be different if they have different response, and then we can find the high risk groups, and fall in this large group, and then take action on top of that, and then that not only just to check the technical performance, then we can also check the impact on the the government debt, and debt duration or debt amount, or those kind of things. So this was implemented in the for the social security, and should save some of technical implemented should save a few hundreds of millions and for government. So there are some other things that are also important to model the impact, and how to model the impact. For example, there's the evolving behavior or interactions between client and government. So we have there's PLN is one of the actions, and then followed by another action, DLC, and then different actions. Then if we quantify their result, or financially result are quite stable, quite similar. But so an important thing for us to understand is that whether they just some of them probably will not make any difference. So the only one is PLN actually probably is the most important. The rest may make no difference, and then we need to ignore that. But so how to define and quantify the impact of each action, implemented by the government on, those clients, and that's certainly important to measure the impact. And then we have ways to, to define the impact, either based on more statistical or the business perspective, and then, to measure with, more and more action or intervention implemented on those overclaim customer, and then we look at from different perspectives, look at their impact, and then find the most important actions and, some of the turning points. And that's really helpful for us to determine, all those response and all actions, some of them actually, take a more important role and, we can measure. And then we'll think about whether we can, particularly focus on those actions, for better impact or high impact. So another important challenge in the real world is that it's a multi-party interactions or collective behavior. For example, so we have the in the social security or tax domain, have a client, and we have this client J may have a partner or family members, and each of them have their individual behavior or behavior sequence, and then lead to either that or not at all. And there could be sequential, behavior or parallel behavior, and then this relationship, between the customers, and then they have their own individual but also related, behavior that's somehow maybe triggered or associated by the parents, for example. And this could be applied to the healthcare as well. The patients and the patients, relatives, they some of the hospital visit or activities could be related to to some of the key primary or patient, and then some follow up actions by different people. And in this way, so we can't just look at one individual patient or one individual customer. We have to put them together, look at the whole party. And then what we do is that we can actually build, a behavioral metrics, and each behavior here actually refer to one person's, behavioral sequence described by, their, activity or time or, the properties of the activity, et cetera, et cetera. And then we can develop for the whole group and over the time period of the behavior, we can develop, ways to model their, within behavior relations or between behavior relations. So to build, formalization for that, and then for the build objective function. And there are many papers we did, for capital market, for pool manipulation. So basically, collective traders, they try to collaborate and how to detect them and evaluate, their impact. And this one is a very interesting one where we did a full government health and look at the overclaim tax and look so when as long as a tax that is created or overclaim is identified, and then we actually have different ways in a non-linear way and to have different actions and triggered to look at the that overclaim and taxpayer, and then after the first purposefully designed action, and we look at the result, and if the result is okay, the data is recovered, that's fine. Otherwise, and the system will recommend another action, the so-called next best action, and then we further monitor the results, and then the person's response, and based on the response, then we further recommend the next best action, et cetera, until when either the data is resolved or when so the data collectors need to be involved to handle the in person. So this kind of technique related to interaction learning and non-linear way, and to involve the domain factors, and as well as the the taxpayers profile and the situation, etc., and then build a system to make the deep recommendations. We use the deep recurrent model and to model their interactions and make recommendations, etc., etc. So that's something I call it actionable, and to really useful for industry. So that's a brief review of some of the relevant work mainly related to myself. And then a second part, I want to more a little bit forward to the current scenario, more related to the bigger data, or so-called data science. So of course, so when we talk about intelligence, of course, we move beyond the data to the wisdom or to intelligence. So one thing we want to do is that, whether we can actually develop, or identify the data mining, knowledge that can really, indicate, that is the best behavior or that's the best action to take. Best means what, and we have to quantify in terms of not only just the technical but also the business perspective. It means it's well lead to the best business impact. Right. So that's something. So when we talk about actionable intelligence, particularly related to the decision making, can support the decision making or business planning to make it better, make it smarter. So those kind of things are called, intelligence in general. So as we know, actually, there are many interesting things there, and we already know, or even I don't know, but other people already know. But there are other things, we really don't know. So that's so-called we don't know what we don't know. So, so what do we mean by that? So there are many actually unknowns, and for example, so often we probably don't know, really what are the distributions in the data, and or what is a hierarchy in the data, or what are the different structures in the data, what are the relationships in the data, et cetera, et cetera. So there are other things more interesting. So we even probably don't know, where are the opportunities or where are the gaps, right? So of course, when I see this could be instantiated into many specific, areas like it related to the scale, or related to the heterogeneity or the different kind of carbon relation, or et cetera, or could it be related to the context, et cetera. So just to give an example, like, the COVID-19 data. So a lot of people say, COVID-19 data is a big data, but to me, actually, it's not a big data. It's actually quite a small data. So usually, particularly for the case numbers, it's actually very, very small. Also very, very noisy and inconsistent. So we compare, many different algorithms we actually find, actually, it's very interesting. So we look at it, probably 12,000, papers on modeling. So we are doing some analysis based on the 12,000 papers we identified related to COVID-19 modeling. So we actually find that the case data is very small, it's very noisy, and the deep learning does not really make a difference. And often deep learning actually suffer from the challenge in such a small data. And everyone knows how we have to consider, the many other contextual factors related to particular, related to either the domain, related to epidemiological knowledge, or, like SIR model, et cetera, all related to the community, the culture, the habit, et cetera. So how to model those things as well. So that shows, the challenge, and sometimes we're lucky and to get something like this, and often probably not so lucky, right? So as we know, so called overfitting or underfitting, etc. So there are many other things to think about as well. So our capability is improving, and an opportunity or challenge to me, I think a lot of case when I see in industry or in working with government, we see actually that actual challenge and potential could be much bigger, and the growth rate may be much higher. So which means algorithms like different neural models may not be really okay. So there are bigger gaps there. So there are many issues we still have haven't really solved very well. So I would not be able to elaborate in more detail, but that's sort of like my qualitative reflection. So there are things I try to categorize and summarize into so-called X complexities, X intelligence, and or X opportunities. So the complexities related could be related to data behavior, domain, or social organizational perspective, or environmental, or human, or network, or learning system itself, or even decision making. So we understand the domain, the data part very well. So like data could be, the different format or different type or different distribution, etc., etc. So it shows sparsity, etc. So like what do we have more, work on, there are many different kind of complexity there. And same, so each of them like a human, the human is part of the system or human is somehow in the, in the system or is in the environment, and how to quantify the human factors or human related, aspects, whether that's necessary. And then if it is necessary, like in the system I just talked about in the text, collection. So unfortunately, we have to work on the human side and understand, the text pairs, circumstance and the circumstance change and their preference, et cetera, et cetera. And we can solve some of the problem. We actually find intelligence related to domain or related to the social perspective, related to organizational perspective. That's more related to the, organization, related to enterprise, and that could be related to human intelligence as well, et cetera, et cetera. Of course, there's a high level framework. There are many things to talk about it. Um, so, and to get them work for the actionable knowledge discovery, actionable intelligence discovery is of course not so easy, and that's why so we'll talk about the human-centered AI or human AI or human machine learning or mining cooperation, and the critical things for this kind of thing that so often so the problem may be not so simple, so we have to go through a qualitative the quantitative process so that we can understand this more and more clear way. And when we work in in industry, particularly for those enterprise, and that's sort of like the process we have to work on. It's not so straightforward. It's just a test or immediately we can develop an algorithm. And often, sometimes we have to integrate the intelligence or address the complexity from different perspective. And the real world case, and I think probably everyone agree, that's often the very complex case. We've got a complex data as we often handle, and then complex behavior, and the model will not be simple as well. And the findings will be interesting, will be complex as well. And then, of course, one of them, and the eventual goal is to identify something that can be really called, insights and can inform the decision making. So then the next half hour also, I want to, illustrate some of the concept related to non-ID learning. What I think, that's particularly a good example to illustrate the complexities and intelligence related to non-ID or system and behavior and data. So this here non-ID is not the concept from the statistical perspective. It is include that, but also go beyond that. So there's some relevant, initially in the community and particularly people from information theory or mathematics or quantum information theory talk about beyond ID, and it means go beyond the traditional ID structure, but also it's not a simple aspect. The opposite of them actually is quite complicated. So there are some of the tutorials with several counting like KDD, IIII, etc., entering in that. So in a nutshell, so I can see that so given a complex data, you could have three objects or three data sources or three modality, O1, O2, 3. And often what we do is that we simplify, we believe, this three data set or three objects, they are IID. It means they are, identically distributed, they are independent, or they are ID drawn from, samples or from the data. So that's what usually we see, ID, right? So the key thing that we have the independence and then we have the identical distribution, right? So that actually, so when we build an objective function for a new object O3, so we find a baseline that could be the center, could be the neighborhood, could be a kernel super plane or a hyperplane, or could be something else. That basically will be the baseline to compare and build the tackle the distance, and then determine whether this is the outlier or whether it's belong to a class, or whether it's in the same cluster, or whether this is a frequent pattern, etc., etc. So that's basically the main things working in the data mining. And but in reality, so they have different shape or different distribution. So it means that we cannot really see the follow the identical distribution. And not only just distributionally they are different, but also there are many other things that really involve the heterogeneity, going beyond the distribution homogeneity. And also they're related, and there's maybe explicit or implicit relationship. And what do we mean by relation, right? So there could be a subjective, there could be a cultural, coupling, and so there's some in cybernetics, in cybernetics and in mathematics, there are some concept called coupling, and then in mathematics, there are some concept called coupling method as well. So actually, I borrow this concept of coupling, and I think there's something interesting to describe the non-identity called coupling plus heterogeneity. So I will illustrate them a little bit later, so related to what I mean by that. So if this is the case, it means the current algorithm like SVM or decision tree and the k-means KN, they won't work. They won't work for this case because they follow the something this IID learning framework. And similarly, so that could be a very interesting question to ask, so whether CNN or RNN or GRU or transformer, and they can handle this kind of non-identity or not. Right? So I think it will be a very interesting thing to discuss and to think. So as I mentioned, the one key thing here is the heterogeneity, and that go beyond the heterogeneous distribution. It could be related to the type, the format, the granularity, and could be related to the rank, to the order, etc., etc. And so look at this. The often will help is that you can have a distribution combine a normal distribution combined with a tail distribution, and you could have multiple distribution. And usually you just use GMM, but when we use GMM, so there's a strong assumption there, and we basically assume that those individual distributions they are independent or they can be combined in a simple way. Right? In some other situation, we add some noise there and describe it, but understanding, we assume that somehow they are not so much covered, right? And this one even much more complicated, and it's not only just the heterogeneity, but also those distributions, they are covered and they are related, and they influence each other. If that is the case, then how to handle that? For example, so I have been working in the financial capital market for over a decade, and working on like a financial crisis analysis, et cetera, by looking across the market, the financial indicators. And you can see actually, some of the financial indicators, they follow a symmetric structure, they follow a scale, distribution, the noise as well, the seasonal factors, the non-stationarity, a lot of things there. And we can't just use a dependence. We can't just use a correlation or association or conditional probability, those kind of things to describe. Unfortunately, we have to consider, the influence of political factors on the financial indicators or the influence of cultural behavior of those traders on the stock indexes, for example. So how to model that? And there are some latent factors there as well, but there are many other things. So related to deep neural models, and we understand there's a very important concept related on representation learning, and typically built on something called decoupled or disentangled. Like in this paper, it's a GAN model and on the disentangled, and this has been quite a popular because we want to see those the factors or features they actually in reality we know they all coupled and they follow their own distribution, they are heterogeneous, and but to make it easy to solve and to interpret, and we try to disentangle them, and we assume they can be decoupled or we can decouple and they are independent somehow, right? So there are many papers, there are many designed, deep neural models follow this kind of principle. But can this really solve the problem? Is this a fair way? Can the result really describe the complexities or the reality in the data? Right? So I just really feel this is a very, very fundamental issue there, and in the current, design, and there are many things related to value relation, related to feature relation, related to relationship. What do we mean by relation? So we use a hidden relation to do the abstraction of over layers. So would that be helpful to capture, the complexity as I mentioned earlier on, right? And when we have the distribution, like in the in the Bayesian, deep Bayesian, yes, we can incorporate the distributional estimation into the deep neural network so that we can go beyond, the point estimation, and to make them more adaptive to the distributional things. So that's good. But so if you have multiple distribution, how to capture that, and how can deep neural models capture, the different distribution? So all these kind of things related to the complexity and related to, the data intelligence, whether we can, and also, related to the contextual, situational factors, how can we model that, or domain knowledge, and to do a much fairer way, to do a much fairer job. And related to the, the relation and the interactions, so we have been working on, the correlations, association, dependence, even causality, uncertainty. All those kind of things are well quantified in mathematical statistics. So there are many other things, like particularly, in the logic, look at model logic. Right? So when we work on the domain ontology, or semantic, or related semantic, so we have to consider that and how to incorporate that into our model, how to learn that, how to extract that, right? So there are a lot of interesting things to work on, and and to it seems like it's still quite a challenge, to model. So there are some other issues, like if we work on the enterprise level and to have, for example, so in a bank, we have the retail bank business, we have the business banking, we have the, the home loan and the credit card, et cetera, et cetera. So can we build enterprise or whole of enterprise, representation, and when we do that, it means we just build for each customer. It doesn't matter where the customer, sit, and we just build our really benchmarkable, representation for all the customers, over so many different business lines in a bank, and so that we can actually really have a comparable a modeling base, or library, or things like that, and we can build for the target based learning on top of that. And this kind of thing actually very, very challenging. Not only just go beyond the data, different data type, mixed data type, or distribution, but also many other things, right, related to the data quality, related to organizational factors, related to social factors, related to customer, related to interaction. So that's some sort of like a things. Like one of project I did for the largest bank here, and I work on the whole of bank representation learning, so that can build some sort of like representation, and for them to to be used for different business lines. And I actually find actually it's quite interesting, but extremely challenge. How about if we don't care about them? And if that is the case, we can find actually so that the results, particularly if we oversimplify, and it just simply assume to follow the ID, and then what we can find actually the result could be really misleading, or could be even incorrect. Right? For example, so this shows on some of the very simple UCI data set the results from different algorithms. So most of the algorithm for this data set, actually are the mushroom ones. Actually, the result actually is wrong. The results are wrong. They do not really capture, the complexity in this very simple data set, and there are much better way to do it. And so there are a lot of such kind of things actually to rethink current, algorithms. Or well recognized algorithms, like, for example, random forest, or decision tree, or SVM, or even the current, deep neural models cannot just take it for granted. And so why? Because there are many aspects for us to consider, like entity, could be related to, the value attributes, the instance, objects, they all share kind of heterogeneity, and then they all somehow have within or between, relation, and then that relation could be related to the mathematical relation, or could be related to cultural or economic relation, or some other subjective relation, and how to quantify that. And there are other things related to interactions or related to the context. So this kind of thing, of course, will be very exciting, but also a challenge as well. And we look at the hierarchical thing from the value of attributes object to attributes and to the final results. It could be a pattern. And there could be relation, affect each other. It may not be just the same thing like, I have to get the object or the data source, I apply algorithm and I get the results, and then that's it. No. So we finally we have to do more. So this could be related to many other things like signal processing, vision, or image, and et cetera, even in statistical learning and many other areas as well. So I just give some examples here. And so one is that for matrix learning. So for example, I go beyond this decoupling or disentanglement in deep learning. So we see, so you get the categorical data could be related to, the semantics or the textual information in a band. And then we see, for the different categorical attributes, or we build the intro or into attributes relation. And then if there's a class there, and then we build the attributes class relation, and there could be many different kind of coupling relation and how to model the coupling, so we can have different coupling functions. And I'll show you next one. So this is a recent paper published, and we actually shows, so for the unsupervised scenarios, you get many attributes, and that could describe different aspects of organization or customer or their interaction, and then we build the coupling space and from different perspective, and then for the converter to the kernel space, and then to for the fuse them and still keep their heterogeneity there, and to build a representation. So basically what we want to do is that, so we have many different aspects to describe the the relations, or what I call the couplings between two aspects, or the two aspects within one higher level aspect, like the value relation within the particular attributes, or the between attributes, two different attributes, and then we can have the object-to-object representation built on top of that, hierarchical multi-aspect, relation, and then we build and to model that. So then we just apply on those categorical data on a very small data, and or the large, like a larger one, and then we compare with different ways, in particular also those like deep models like Bayesian or VAE based, and then you can combine with different learner like wet and wide or wet and deep or some other neural models. That's just application otherwise. And then we can compare the performance. You can see those deep models, they cannot really capture them well, and there's good reason to explain that. And then you look at the realization, you find actually they cannot really split like by again, and so there are better ways to to find their relation, and then represent their relation, their heterogeneity, and then so that we can make them more separable. And another concept I want to quickly highlight here is that related to recommender system. We know in recommender system we have the user, user and their demographic and item properties and the rating. Usually we work on the rating, and then so over the decade, there are many different concept proposed in recommender systems. So I call it different generations, from fourth to fourth generation, work on many different concepts. So everything there actually is look at the user relation, and treat the users as non-ID, and treat the items as non-ID, and treat user and item interaction that could be implicit, could be explicit, and they actually jointly affect the rating behavior as well. Right? So look at from this way, I actually find so something becomes so clear to model the recommender system in a much more thoughtful way. And for example, so one thing model the attraction. So how to so there are more ways, and why this more attract me, is that because of the story, or is that because of the customer members, and how to model that, right? So you go to the member related, customer related, and for a particular user, and also have the movie story, and then we can build their the attractions of the story description from the word to sentence to story level to that particular user. And then same we can do that for the member and the cast, and then combine them together to learn so why a movie attract is attractive to a particular user, and highlight and highlight to see the reasons related to the distribution, or to the to the word level, or to the cast members, etc., etc. I think I better leave some time. So just quickly, this one. So the statistical things. So for example, so when we model the large scale recommender system, so look at recommending and basically do the rating, and but we involve the users information, and the attributes and the values, and also look at some of the particular challenge, like sparsity, different kind of sparsity, there user sparsity, rating sparsity, and there are different types of sparsity, and also the relation, and how to incorporate that, and as well as consider this in a dynamic way, and to model this whole thing, how the rating is generated, and related to the user or to the item, and with different factors, by also involve the metadata as well. So and by doing that, and we show so whether that actually could be helpful, and in terms of the modeling or the recommendation, for example. So those are perspective goes beyond the new or code style issue, or sparse recommendation issue. So usually what will happen is that, so when we see those kind of new items, the code style very sparse and rarely visited, and then rarely will be readily recommended, and by looking at their more complex item or user level interactions, and then we can have a much better way to recommend, and also the recommendation will be more personalized, will be more relevant, and we can also monitor the behavior, like a person listen to different music, this two-person listen to pop or rock music over time, and then we recommend the music and to them over time, and see whether by looking at the user item, their specific perspective, and also their interaction and relation, or their influence on the rating, whether we can make a better recommendation of the music. So I skip the outlet detection. So there are a lot of books there as well. So there's some other related to intent learning, and intent, I say, I can model the intent using the biomedical way to model the intent, and there are other things like for recommender system in basket analysis, by a basket of B1, B2, B3, different basket over time, and whether there are some relationship there, and why I buy this particular Panadol, for example, and after purchase Band-Aid and those kind of things, they're in driving factors, and how to model the hidden driving factors, etc., etc., and then build some of the different models and intention unit to model the long term and short term intention that could affect the item selection in each basket, etc., etc. And recently, of course, we know that automated machine learning has become so popular. So, so how to make automated machine learning actionable, and not only just recommend and do the give us, a combination of the process or the selection of the algorithm or even the algorithm architecture, et cetera, et cetera. But also make sure, the result could really be used to change the behavior or to inform, the next best action, et cetera, et cetera. So for those kind of things, we have to really measure the actionability, and that need to consider the domain factors and or social or other business factors, and incorporate that into the model. And sometimes it could be the result or the effect. We have to consider the impact or the effect and how to model that in the modeling process. So that's quite different from the Euro way, because the Euro way is that we model, what we are given, and then to do the prediction on top of that. So that's it. So overall, I want to highlight, of course, the domain knowledge and the domain specific, applications are very important, and have to consider the domain factors and complexity intelligence. But I go beyond that. I think there are many other things related to social, related to human, economic, culture, personal factors of complexity intelligence. So related to behavior, for example. So there are many things related to the interaction as well. And when we characterize, the complexity or intelligence, particularly from a complexity perspective, and we can look at a more specific, the challenge related to the, related to each aspect, like data complexity or the behavior complexity or the human complexity. And of course, the goal is to identify, discover, something called knowledge that I can discover, some of the insight, but also it would be good if we can deliver something that can actually be directly used for decision support, and if that application can actually lead to impact, like save some money or really make some change. And of course, this is really a challenge. And today I just illustrate one aspect related to some particular aspect called a non-ID or beyond ID, but there are many other things to discuss. So sorry, so I think I stop here. So I'd like to hear any comments or suggestions or any questions from the from the audience. Thank you very much.